Okay, so this practice problem is going to look at the superposition of electric fields of 2 point charges. So I have a positive charge and a negative charge. They're both along the horizontal x-axis. Charge 1 is 6.2 microcoulombs. Charge 2 is negative 9.5 microcoulombs. Charge 1 is at the origin, and charge 2 is at 10 meters. What is the electric field at a point x equals to negative 4 meters? So both of these charges have the potential of influencing the space at negative 4 meters. How do they work together to get the net field at that location? All right, so let's first make a guess. It's always sometimes a great idea to sort of get an idea. What do we expect the electric field direction to be at negative 4 meters? Just to do some conceptual understanding first. So what would be the direction of the electric field at x equal minus 4? Well, we use a test charge for that, remember? So whenever we're kind of looking at electric field direction, we use that positive test charge. If I were to put a positive test charge at this location, I have a positive charge and another positive charge. That's going to be a repulsive force. I know the electric field by this is pointing outwards. So a positive test charge will feel a force in the outward direction. And so by this charge, charge 1, I would expect the force to be in the rightward direction. What about from charge 2? Well, in the case of charge 2, the electric field lines are pointing inward. A positive test particle would be in the inward direction. Now this is a larger charge, and so the influence at any given radius may be larger than my 6.2 microcoulomb charge, but it's pretty far away, and we know that the electric field is dependent on the square of the radius. So we probably are going to expect that the force on my test charge is going to be smaller from charge 2, my negative 9.5, than from my positive 6.2, which is closer. So we may expect the electric field to be pointing to the right at negative 4, but probably of a smaller strength. So given that, I have a larger strength electric field to the left, a smaller strength electric field to the right. So we may predict that my net electric field at that point will be pointing left. So let's see what happens. All right, well, just like with superposition of forces, and when we calculate the net force, to determine the net electric field, we can look at each of the electric fields individually and then put them together vectorially. All right, so let's look at the electric field for charged particle 1. We know that the electric field is K times Q1 over radius 1 squared. So, of course, my K is 8.99 times 10 to the 9th. The charge on Q is 6.2 times 10 to the minus 6th coulombs. And the radius between where I'm interested and the particle, and the charged particle, is 4 meters. All right, so the strength of that electric field is I have these all in meters. This is in centimeters, or my answer key isn't going to work out so well. Let me rephrase. These are centimeters. Put meters, and I looked at that order of magnitude of my key, and that wasn't going to work out. So it's not 4 squared. It's 0.04 quantity squared. All right, so the magnitude of the electric field at 4 centimeters to the left of charge 1 is 3.57 times 10 to the 7th, 3.5 times 10 to the 7th newtons per coulomb. Sometimes I think I'm better if I just do the calculations on the fly. That's the magnitude, but what about the direction? Because when we're going to superimpose these, so superposition of these, the direction matters. Positive charge, field lines point out, pointing out at this location means pointing to the left. So we're at 3.5 times 10 to the 7th newtons per coulombs at 180 degrees. We're pointing to the left. All right. What about for charge 2? Well, for the charge 2, the electric field of 2 is going to be K Q2 over R2 squared. So that's 8.99 times 10 to the 9th. Charge Q has a magnitude of 9.5 times 10 to the minus 6th. And the radius is 0.1 squared. So my magnitude of charge 2, the magnitude of the electric field, is 4.4 times 10 to the 6th newtons per coulomb. Now, because this is negative, that's going to give me a direction that is towards. So my positive particle is going to feel a force towards that charge Q. The field lines point towards the charge. So this is a magnitude 4.4 times 10 to the 6th at 0 degrees along the x-axis. All right, so now I have a contribution of the electric field from particle 1 and a contribution of the electric field from particle 2. So I add them vectorially. When I add things by vectors, we have to break them up into their horizontal and vertical components. So we'll call this field 1. That's the contribution of field 2. Horizontally, field 1's at 180 degrees. So minus 3.5 times 10 to the 7th. There's no vertical component. The second field is at 0 degrees, so positive 4.4 times 10 to the 6th. Again, there's no vertical component. And so I can add these two up to get my net field, and negative 3.5 times 10 to the 7th plus 4.4 times 10 to the 6th gives me negative 3.1 times 10, that's not a 1, negative 3.1 times 10 to the 7th newtons per coulomb. What does that negative tell me? It tells me that the electric field is pointing at 180 degrees, like we predicted from the beginning, with magnitude 3.1 times 10 to the 7th newtons per coulomb. All right, so I have 2 point charges. I can sum those point charges vectorially, so looking at the influence of each one of those point charges individually and adding them up vectorially, and I get the magnitude of my electric field. What would have happened if my charged particle was located maybe up and to the right of charged particle 1? Well, if that were the case, I can still determine the magnitude of that electric field with the radius between the two charged particles. Through that same method, I would need to figure out the angle of that electric field so that I could break the contribution of the electric field by particle 2 on this location into its horizontal and vertical components. But the process is the same. I then have the horizontal and vertical components of the net electric field. We can use Pythagorean to put it back together and to find the angle using the inverse tangent of the electric field at that location. So no matter how many point charges I have, I can pull them apart individually and then put them back together in terms of adding those electric fields, the superposition of those fields. All right, good job.